In this final video for Chapter 21, we'll go over other alpha carbon reactions. We'll talk about thermodynamic versus kinetic enolates and how they can be used in alkylation reactions. We'll talk about the malonic ester and acetoacetic ester synthesis, go over a summary of the bases, and then talk about simple versus conjugate addition reactions. And then specifically tied to the conjugate addition, we'll talk about the Michael additions and the Stork-Enamine reaction. Now we know that the strong bases such as sodium hydride and LDA are capable of forming irreversible reactions to make enolates. So now when it comes to an asymmetrical ketone, each base is very specific about what type of alpha hydrogen it is going to remove. So if we consider this asymmetrical ketone here, we have several different hydrogens or alpha hydrogens that can be removed by our bases. So we have a single alpha hydrogen here that I'll put in red, and 3 over here to choose from that I'll put in orange. Now the sodium hydride is always going to remove the hydrogen from the more substituted carbon. So in this case, our sodium hydride will remove the alpha proton that is in red. So it'll come over and give the electrons to the alpha carbon. Now the reason that it does this is because if we take a look at the enolate that forms, we have our lone pair on the more substituted carbon. Now we know that enolates are capable of being stabilized by resonance, so let's go ahead and draw the resonance structure for this enolate. So now we have formed a double bond in our resonance structure that is more substituted than the double bond that would form on the least substituted carbon. So the more substituted double bond is actually the more stable product. And this is known as the thermodynamic product. Now this product is capable of forming mostly because the hydride ion is so small, it's capable of accessing this alpha hydrogen. Now LDA, which is a much bulkier base, cannot come in and remove this alpha hydrogen. So instead, the LDA is going to remove one of the easily more accessible hydrogens, which are the orange ones over here. So the LDA will remove the orange hydrogens. That again is going to form an enolate, but now the enolate is going to be on the least substituted carbon. And again, this is stabilized by resonance. But as we can see, we've formed a double bond that is less substituted. So the least substituted double bond corresponds to the least stable enolate product. However, this product forms very easily and very quickly, so it's known as the kinetic product. So in summary, sorry, I'll go ahead and erase this here. Thermodynamic enolates are favored by strong, unhindered bases, such as sodium hydride. Now, because we need a higher temperature and heat to kind of push this reaction to completion, we're going to run these reactions a little higher temperature at room temperature of around 25 degrees Celsius. Kinetic enolates, which form a lot quicker, are favored by strong, bulky bases such as LDA, and we typically run these at low temperatures since this reaction doesn't require as much energy. So you're typically going to see sodium hydride associated with 25 degrees Celsius and LDA associated with minus 78 degrees Celsius. And this is really just kind of giving us hints as to what type of enolates are going to form. Now, once the enolates form, they're capable of acting as nucleophiles, and we can actually undergo alkylation reactions. So for instance, in the presence of an alkyl halide, our enolate will come, attack the R group, and kick off the leaving group. Now this is an SN2 mechanism, so we must be dealing with a methyl primary or secondary alkyl halide in order for these reactions to occur. Now in the end, we will add an R group and form a new carbon-carbon bond. So let's go ahead and take a look at the different types of reactions that would form if we use different conditions for an asymmetrical ketone. So first, let's go ahead and see what type of reaction or what type of product would form when we take this ketone, treat it with sodium hydride at 25 degrees Celsius, followed by ethyl bromide. Now with sodium hydride, we know it's going to go to the more substituted carbon. So we're going to be removing this alpha hydrogen here. The enolate will go at this alpha carbon and will attack the ethyl bromide, kicking off the bromine as a leaving group. So we will end up with a product that looks like this. If we were to take the same reactant and treat it with LDA at minus 78 degrees Celsius, followed by again the ethyl bromide, we know that the LDA is going to go to the least substituted alpha carbon. So it'll remove one of the two alpha hydrogens here, and the enolate will form on this carbon there. That again will go and attack the ethyl bromide and kick off the bromine as a leaving group. And we end up with this product here. So you can control which product will form when you're dealing with asymmetrical ketones by choosing the appropriate base. The next reaction we will discuss is the malonic ester synthesis, and this reaction is specifically for making carboxylic acids from alkyl halides using diethylmalonate. Now what we're going to be doing ultimately is adding 2 carbons to the alkyl halide as well as turning it into a carboxylic acid. So first, diethylmalonate is a beta diester. Which has this structure here. Now this molecule has 2 alpha hydrogens that are highly acidic. So because they are surrounded by 2 carbonyls, they have pKa's of around 9 to 10. So now when we put this molecule in the presence of sodium ethoxide, the base will remove the alpha hydrogen and it will place the enolate at this alpha carbon here. Now this enolate will be highly stabilized by the 2 carbonyls. Now at this point, the enolate can act as a nucleophile, just as we saw with the previous alkylations, and we can put this in the presence of an alkyl halide, such as ethyl bromide. So this will allow us to attach an ethyl group at that central alpha carbon. So we're adding 2 carbons here. So these are our 2 carbons. Next, we will treat this molecule with H3O+. Now H3O+ is capable of turning esters into carboxylic acid. So we saw that in chapter 20. So this is our acid-catalyzed hydrolysis of esters. And we're going to convert both of these esters into carboxylic acids. Now, in the presence of heat, we can actually lose one of the carboxylic acids in a process called decarboxylation. Now, I'll go ahead and number the carbons so we can see what's going on. And it doesn't matter which of the carboxylic acids we're losing, but I'm going to go ahead and show the loss of the carboxylic acid attached to carbon number 5. Now, ultimately, for our final product, we have formed a carboxylic acid. From an alkyl halide, we've added 2 additional carbons as well. So on the next slide, we'll take a look at the mechanism for decarboxylation. So I'm going to start by drawing the intermediate right before the decarboxylation. Now what I'm going to do is redraw carbon number 5 by rotating it around, and I'm also going to show the OH bond drawn out. Okay, at this point, we have the molecule all set up for the mechanism. So what's going to happen is the oxygen attached to carbon number 1 is going to go and remove the H from the carboxylic acid attached to carbon number 5. That is going to cause the bond between the oxygen and hydrogen to break and form a new double bond between carbon number 5 and the other oxygen. That is going to cause the bond between carbons 2 and 5 to break and come over and form a double bond between carbon 1 and 2. So this is a very favorable mechanism because we have a 6-membered cyclic transition state. And as we know, the 6-membered rings are the most favorable size. Now, after this mechanism, we will have an intermediate that looks something like this. Now, this is in its enol form. So we have an ene and an ol. So we know that enols are capable of tautomerizing. So we're going to see a very forward arrow of tautomerization. And the mechanism for the tautomerization will be same as the mechanisms that we saw in previous chapters. Ultimately, the enol will convert to a carbonyl, and we will get our final carboxylic acid. Let's go through a couple of practice problems. For the first one, which carboxyl group will undergo decarboxylation? A, B, or both? Now, in order to answer this, we have to consider the mechanism we just saw, which included the 6-membered cyclic transition state. Now, that transition state is key for decarboxylation. Now, in order for that transition state to occur, the carboxylic acid must be a beta carboxylic acid, meaning it shares an alpha carbon with another carbonyl. So let's go ahead and take a look at carboxylic acid A. So here we have an alpha carbon, and it's sharing the alpha carbon with another carbonyl. So technically, this is the beta carbon for our ketone here. So this is defined as an alpha beta carboxylic acid. So we do have a carboxylic acid for A. For B, this is the alpha carbon here, and these are the beta carbons. Now, none of the beta carbons contain any carbonyls, so B is not capable of achieving that 6-membered transition state. As a result, B cannot undergo decarboxylation. So if we were to treat this molecule with heat, we would only lose group A. Group B would stay as a carboxylic acid. Now let's work through the predict the product for number 2. We're starting with diethylmalonate, and we have a multi-step synthesis. So starting off, let's take into account every single step here. Step 1 is we have sodium methoxide. Now we know sodium methoxide is going to remove one of the alpha hydrogens. Now in diethyl malonate, there are 2 alpha hydrogens. Once we remove it, it's going to form the stabilized enolate, which can then act as a nucleophile and react with this alkyl halide, methyl iodide. So after our first 2 steps, we're installing a methyl group on the alpha carbon. Next, we're treating it again with sodium methoxide. Now again, this is a base, and we still have an alpha hydrogen that's capable of being removed and forming an enolate. Once the enolate forms, we'll react it with the ethyl bromide, and so here, after step 4, we're installing an ethyl group. For our final step, H3O+, we're converting our esters into carboxylic acids, and heat is allowing decarboxylation to occur. Now, it doesn't matter which carboxyl group we lose, but we know that we're going to lose one of them. In the end, we will have a carboxylic acid with the methyl group attached and an ethyl group attached. So these type of multi-synthesis or multi-step syntheses are possible with the diethyl malonate. Now related to the malonic ester synthesis is the acetoacetic ester synthesis. The purpose of this synthesis is it's going to make methyl ketones from alkyl halides using ethyl acetoacetate. This reaction will add 3 carbons to the alkyl halide as well as the methyl ketone. So this is also a carbon-carbon bond forming reaction. Now the ethyl acetoacetate has a similar structure to the diethyl malonate. However, instead of having 2 esters, we have a ketone functional group and an ester functional group. So now let's go ahead and take a look at a multi-step synthesis similar to what we saw with the diethyl malonate. So I'll go through each of these steps and then show the final product. So for step 1, we know that we have sodium methoxide, and here again we have highly acidic alpha hydrogens. So the purpose of step 1 is to form our resonance stabilized enolate. For step 2, we're putting our enolate in the presence of methyl iodide, which is our alkyl halide. So we know that this can act as a nucleophile, kick off our leaving group, and we will add the methyl group to our alpha carbon. Then we're using H3O+. Now I'll leave the heat out for the moment, but H3O+ is going to convert our ester to a carboxylic acid. And lastly, the heat is going to cause decarboxylation where we're going to lose the carboxylic acid only. The methyl ketone will stay in place. And this is our final product where we have a methyl group. We have added 1, 2, 3 carbons and as well as a methyl ketone. So very similar type of product as with the malonic ester synthesis, same types of steps in terms of the mechanism, it's just we're forming a methyl ketone instead of a carboxylic acid. Now we've gone through several bases in a lot of these reactions, and I just kind of wanted to give a summary of when you should use which base with which reaction. So in general, the aldol reaction, aldol condensation, utilizes sodium hydroxide. The Claisen, malonic ester, and acetoacetic ester syntheses all involve sodium ethoxide. The thing that these guys all have in common is all these reactions involve esters. Now the haloform reaction also involves sodium hydroxide. Alkylations, because we need to form enolates irreversibly, involve LDA or NaH, depending on where we want to install the alkyl group. The directed aldol involves LDA, and that's so that we can form the enolate and have it react selectively with another aldehyde or ketone. Then we haven't yet talked about the Michael addition, that's next, but the Michael addition involves sodium hydroxide or potassium hydroxide. In preparation for talking about the Michael addition reactions, I want to go over simple versus conjugate addition. And specifically, we're going to be talking about a nucleophilic attack on an alpha-beta unsaturated carbonyl. So an example of an alpha-beta unsaturated carbonyl is this conjugated ketone. So for our ketone, we have an alpha carbon and a beta carbon. So that's why we have alpha beta. Unsaturated means that the carbons don't have as many hydrogens as they're capable of having. So whenever you have a double bond, it's capable of accepting more hydrogens, which makes it unsaturated. So that's how we get the term alpha beta unsaturated carbonyl. Now these molecules are capable of undergoing resonance. So for our first pattern of resonance, we have a pi bond between two atoms of different electronegativity. So once the pi bond moves up onto the oxygen, we end up with our first resonance structure. Now we've created a resonance structure that has a allylic carbocation. So the electrons will come over towards the positive charge, and we will create our third resonance structure. So now if we consider the hybrid resonance structure, at any given point, we can have a double bond between the oxygen, the carbonyl carbon, and the alpha and beta carbon. So I'm going to draw a dotted line to indicate that partial double bond character. Now also at any given point, we can have a positive charge on the carbonyl carbon or a positive charge on the beta carbon. So that means that positive charge is delocalized across those two carbons. So those positive charges are electrophilic. They attract nucleophiles. So a nucleophile has a choice. It can either attack at the beta carbon or it can attack at the carbonyl carbon. Now an attack at the beta carbon is called conjugate addition. Attack at the carbonyl is called simple addition. We'll take a look at these mechanisms on the next slide. So giving an example of simple addition, we'll start with our alpha-beta unsaturated carbonyl. Now I will use a generic nucleophile with a negative charge. Now with simple addition, the double bond, the conjugated double bond, is not going to move at all in the mechanism. We are simply going to have the nucleophile come in, attack the carbonyl carbon, and kick the electrons up onto oxygen. And we've seen this type of mechanism several times before. Now we've added the nucleophile to the molecule. Now at this point, we can treat it with a proton source to turn it into an alcohol. And again, the double bond did not move at any point. So this is our simple addition product. For conjugate addition, we do involve the double bond. So with conjugate addition, the nucleophile is going to come in and it is going to add to the beta carbon, because that's the one that has the partial positive charge. That's going to cause a cascade of electrons. This double bond is going to move over and then it's going to kick up the electrons onto the oxygen. So we've now added the nucleophile to the beta carbon. Now at this point, if we supply a proton source, we will protonate that oxygen. And now we have an enol product. Now we've learned that enols are capable of tautomerizing to ketones. So we will have the tautomerization occur, and our enol will turn into a ketone. And we get our keto form. Now the way that we can predict whether an alpha-beta unsaturated carbonyl is going to undergo simple versus conjugate addition is by looking at the strength of the nucleophiles. In general, simple addition is favored by strong nucleophiles, such as Grignard reagents, whereas conjugate addition is favored by weaker nucleophiles. So for example, if I were to take my alpha-beta unsaturated carbonyl and treat it with our Grignard reagent, such as methyl magnesium bromide, followed by water as a proton source, then because the Grignard reagent is such a strong nucleophile, it's going to attack immediately at the carbonyl carbon. With the conjugate addition, there's a lot of electron movement involved. So strong nucleophiles just want to do their nucleophilic attack and have the reaction be done. So with Grignards, we're going to see a direct attack at the carbonyl. And ultimately, the oxygen is going to be turned into an alcohol. So with Grignards, and we've seen this in lots of previous chapters as well, with Grignards, we're going to end up making an alcohol as well as a new carbon-carbon bond. And this will be our major product. With weak nucleophiles, and examples of those can be cyanide ion, amines, or Gilman reagents, those are going to be the ones that undergo the conjugate addition. So we'll take a cyanide ion, and because it's a weak nucleophile, it will do the conjugate addition, adding to the beta carbon and starting that cascade of electrons. Now, once we supply a proton source, such as hydronium, we will protonate the oxygen, create an enol, and then it will immediately tautomerize. Into a ketone. So Michael additions are specific types of conjugate addition reactions between stabilized enolates, and the stabilized enolates are acting as our weak nucleophiles, and the alpha-beta unsaturated carbonyls. So for example, if we were to take a stabilized enolate, such as this beta diketone, and an enolate is when we've already removed the alpha hydrogen. So these lone pairs are stabilized by resonance between these two carbonyls. Now this enolate acts as our weak nucleophile. And in this type of reaction, this is known as the Michael donor. Now when we put this in the presence of an alpha-beta unsaturated ketone, we have the same type of conjugate addition reaction occurring. The electrons will come over, attack the beta carbon, and cause the cascade of electrons. Now, this alpha-beta unsaturated ketone is known as the Michael acceptor, since it's accepting the electrons. Ultimately, we are creating a new carbon-carbon bond between two fairly large molecules. So our new bond is located here. Now, once we take this molecule and supply a proton source, we will protonate the oxygen, turn it into an enol, and then again, it will tautomerize into a ketone. So Michael donors can be any sort of stabilized enolate. So this is the conjugate base of the diethylmalonate. So this, once the enolate is formed, is stabilized as well. So this can act as a Michael donor. Gilman reagents can also act as Michael donors. They are weak nucleophiles. Other types of Michael acceptors, so things that act similar to the alpha-beta unsaturated carbonyls, is this type of conjugated cyano group. So we have a double bond here, one bond away from a triple bond. So this can undergo resonance as well. And sometimes this molecule is drawn like that. You can also have unsaturated carbonyls with amides. So it's not just for ketones. You can use amides, esters, etc. So these are just other examples of molecules you would see in the Michael additions. Enamines can also be used as Michael donors. So an enamine we learned about in chapter 19. I'll just go through the process of creating an enamine. So we start with a ketone. We use a secondary amine. We run this in the presence of an acid catalyst. So this is going to be our enamine formation. Now an enamine is capable of undergoing resonance. So we can have these electrons come down and form a double bond and kick our double bond as a lone pair onto the carbon. So these lone pairs act as a stabilized enolate. So now at this point, the enamine can act as a Michael donor. So putting it in the presence of a Michael acceptor, such as this alpha-beta unsaturated ketone, we can see the conjugate addition occurring. Oops, I forgot my positive charge. Now we can use H3O+, and the H3O+ is going to do two things. H3O+ is used to remove an enamine or an imine and return it back to a carbonyl. So this H3O+ will protonate the oxygen and create an enol. Then the enol will tautomerize. Then the H3O+ is also going to convert the enamine back into a carbonyl. So at this step, it converts both of the groups to carbonyls. So you end up with a product that looks like this. Now you may ask, what's the purpose of drawing a molecule that looks like this? Well, this type of reaction can continue, and we're going to see this type of reaction in the lab as well. So if we were to treat this molecule with a base, such as sodium hydroxide, and heat, we will actually have an intermolecular aldol condensation occur. This is also known as a Robinson annulation. The term annulation means ring forming. Now it's the same mechanism as what we saw with the intermolecular aldol reaction. The sodium hydroxide is going to remove the alpha proton from the end of this carbon here. This carbon will attack the carbonyl carbon and will ultimately form a 1, 2, 3, 4, 5, 6-membered ring that's going to be fused with the other 6-membered ring. You can go ahead and attempt that mechanism on your own, but we will end up with a product that looks like this. These types of reactions are very useful to form molecules that have steroid backbones, which we will see in our last learning unit as being very important in nature.